Hello everyone, welcome to our channel. In this channel we try to talk about the most trend papers and subjects in the field of deep learning, and we hope that you find them useful. For today we selected this paper, Conditional Channel Gated Networks for Task-Aware Continual Learning. And before we jump into the paper, let's see together what continual learning means. So continual learning is a way of making deep learning models learn new things over time without forgetting what they already learned before. For example, imagine a model that has been trained for task 1 and can recognize objects from this specific data distribution with good performance. In continual learning, we want to train the model also for the task 2, which has a different data distribution, so that the model can recognize the new objects while we don't want it to forget how to recognize the old objects. And the same for the new tasks like task 3 and task 4. However, there is a challenge with continual learning using conventional methods, which is called catastrophic forgetting. Catastrophic forgetting happens when a model forgets what it learned from previous tasks when it learns new tasks. It means that when the model learns a new task, it loses its performance on the old task. This happens because when the model learns multiple tasks sequentially, gradient descent can cause the model to overwrite the parameters that are important for the previous task. This is because gradient descent only considers the loss function for the current task and ignores the loss function for the previous task. Therefore, the model may change the parameters in a way that improves the performance on the current task but worsens the performance on the previous task. So let's get to this paper. This paper offers a method to prevent catastrophic forgetting. Let's look at the methodology here. The idea is that for each task, we use a subset of kernels and freeze the others, which is kind of dividing the capacity of the network for different tasks. But how do we identify important kernels for each task? In a neural network, between each layer and the next, we have convolution that results in a feature map that summarizes the presence of the detected features in the previous layer. And the idea is that we should connect each convolution to a gate module. This gate takes the feature maps from previous layer and takes global average pooling for each channel. Let's say we have n channels, so we would end up with n values, and each value represents the whole corresponding channel that will be passed through a fully connected layer, and the output would be given to a Gumbel noise while the activation function is Gumbel softmax. And the Gumbel softmax decides which kernel should be on and which kernel should be off or unused. Then we take the gate output and multiply it with the feature set, and where the kernels are black or off, the weight is 0, so the kernels would not be trained. And those kernels that are white or on will be trained. So using gate modules during training time, the network learns which kernels should be trained and which should be frozen. Okay, let's assume that we have T tasks with T gates. The feature sets for kernels are shared between all tasks, so they are all the same. But the gates are the ones that are different for each task, and they are the ones that decide which kernels should be selected for each task. So the final candidate feature maps would be unique to each task. Another important part of the backbone architecture is the end of the network, which is the task classifier. But why do we need the task classifier? Let's remember that we have T tasks and T outputs. In the inference time, the labels for each task are unknown, As a result, the network doesn't know which task to solve. And the task classifier helps to find the head output that can be trusted. But how does it work? So all the T candidate feature maps that passed through the T gates in the previous stage would be transformed using a global average pooling, and then will be concatenated and passed through some fully connected layers. And that would result in probabilities for each task. Whichever task that has the highest probability at the end would be the one that should be solved. For example, in this case, the probability of task 2 is the highest. So the head 2 output would be the one that can be trusted. To summarize, the goal is to prevent catastrophic forgetting and having computational efficiency. To do so, we need to decide which subset of kernels belong to each task. To do that, we use gating modules. The gating modules dynamically select and freeze relevant weights for each task. Let's say if we have 30 kernels, using gates, we would know which of them are actually important. And at the inference time, since we don't know the labels of each task, we need to use a task classifier that translates the feature sets to probabilities for each task and decide which task should be solved. If you are interested to know about the experimental results that show the effectiveness of the proposed method, please check out the paper using the link provided in the caption. And also let us know which topics you're interested for next time. Thank you and see you next time.